Okay. Okay, let's pick up from where we left yesterday. Huh? Okay. So yesterday we started learning how to do real integrals using contour, using the trick of contour integration. Okay. So one type of integral that we learned was integrals of the type this. So if I have an integral whose limit is from minus infinity to infinity, okay, it may be possible to do this integral by considering a contour integral like this, dz over a contour c f of z, okay, right, and the contour that you consider is basically you take one part of the contour to be the straight line and the second part to be this to be a circle of radius r, okay, then you set okay, this is from minus r to r. So one part of the contour you take to be this straight line, right, along the real axis, and the other part the semicircle of radius r, capital R, then you set r to infinity, okay. So on the straight line y is 0, so z is just x, okay. So this integral can then be split into two parts, minus infinity, once I taken r to infinity, minus infinity to infinity dx f of x, which is the integral I need, okay, plus integral what, 0 to pi, excellent, and I will get what, I will have dz, but dz lies on the circle of radius r, right. So here I get r I e power I theta d theta and f of r e power I theta. Huh? Remember dz you have to take according to the curve that you are integrating over. This curve is a straight line, okay, along the x-axis, so y is 0, so dz is just dx. This curve is a circle, so z is r e power iota theta, right. So there will be an equation for the curve, and then from there you will get by differentiating then what dz is. So that's why you get this entire thing r iota e power iota theta d theta is dz, and there is your function evaluated at what z, which is this r e power iota theta, the theta point here, this point, okay, the function evaluated there, okay. Now what did we do afterwards? That this part is what I need, okay, and this part I want this part to vanish, okay. And what was the condition that we derived for this part to vanish? That mod f of r e power iota theta, that this guy should kill the function of as r approaches to infinity, okay. It should kill the function of faster than r makes it grow, right. So it should be much less than what, 1 by r, right. It could be e power minus r, e power whatever, as long as this decay is faster than the r growth, right. Then this part will vanish, okay. And all you are left is this. So integral over this contour is just the integral over the real line, okay. So you doing this contour integration by splitting into two parts recovers the integral that I need. But contour integrations we know are very simple to do. You just need to figure out what singularities are inside the contour. Let us say it has a singularity here, 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 and then compute the residues, right. For simple poles, this residue is given by this formula, limit z approaches to zi. So there would be a 2 pi I, because the integral is 2 pi I times the residue, z minus zi f of z, right. So zi is the point where the singularity lies. Then you need to sum over all, right. This is the residue at z equal to zi, but then you need to compute residue at all points. I runs from 1 to, let us say it has n, right, okay. So from there we learn the basic principle of this doing real integrals using what, contour integration, is to write down a contour integral okay, which when split into parts gives me back the real integral, and rest either vanishes or you know how to compute that. Okay, fine. You realize that I will tell you one more example where you know how to compute the remaining part, right. Let us say this did not vanish, okay. But typically this will vanish, okay, but in certain cases we will take, I will show you that we will take different contours, right, slightly deformed contours of this, okay. There it will not vanish, okay, but the extra parts, basically whatever extra parts you get, they will not vanish, but they would be something that you can compute, okay. Then you can take all this on the other side and you will still recover your integral, okay. Is that clear? But for now this guy should vanish, only then my integral would just be sum of residues, okay, and this condition needs to be met. So whenever you are given an integral of this type, you do not need to do all this exercise, all you need to figure out that whether this guy vanishes on the circle. Once it no, just look at the residues, sum, and that gives you the answer, okay. Obviously residues in the upper half of the complex plane. For now we are assuming that this vanishes here, so upper half of the complex plane, okay. There would be cases where you would be forced to close it on the lower half. It won't vanish on the upper half, but it would vanish on the lower half. So then you would need to close it on the lower half, but the theory would be the same, right. Then you need to compute what residues in the lower half, right. So integrals of this type, let's say let's do this integral minus infinity to infinity d dx 1 divided by z to the power 5 plus 1, okay, right. So how does this, okay, no, z to the power 5, x to the power 5, okay. Now think of this integral over this circle, right. So I will have r to the power 5 here and r from here, the major, right, remember. This is the real integral that I have to compute. No, but I know I want to use the residue theorem. Basically residue theorem is that only, that the integral over any closed curve is sum of residues inside, okay. I want to use the residue theorem, okay. So for that the contour I consider is this, okay, and then I need to think about whether it vanishes on the upper half, on the circle. On the circle this dz would be r e power iota theta, right? So what will this guy go as? R to the power 5, right, yes, as r becomes large and large, right, the denominator, and numerator has just r. So this, there is an overall decay of 1 by r to the power 4. So we are good enough to go. So what do I need to compute? Poles, right. I need to figure out what kind of poles it have. Will it have poles or will it have essential singularities? Poles, it's a polynomial, 1 by p of z. 1 by p of z, where p of z is a polynomial, it always has poles, right, at what? At the points where this polynomial has what? Zeros, exactly, right. And these poles would typically be of simple poles, right, except when you repeat a root, right, then it would be whatever, how many times you repeat, that order would be the pole order, okay. So how many poles does this function have? If you think of it on the complex plane, no, this is a real function, but if you think of this on the complex plane, z to the power 5 plus 1 f of z, how many? 4, 5, right, 5, right. So points where z to the power 5 plus 1 is equal to 0, this is a polynomial of order what? 5. So how many roots does it have? 5, okay. Okay, I hope none of them is on the real line, because then this is not nice, but let's assume that none of them is on the real line, okay, right. We'll discuss what happens when if there is a pole which is on the real line, okay. But for now, for now just ignore it. Let's just say that none of them are on the real line. Oh no, wait, if z is minus 1, then that's the root. Minus 1 to the power 5, minus 1 to the power 5 is minus 1, so this has a pole on the real line, okay. let's let's do some, yeah, let's do something about it. Let's put x square here. Yeah, so plus z square. Okay, good. So now hopefully there would be no pole on the real line. Okay, once again I'm just assuming. Okay, huh? So how many roots does this have? 5, right? So let's call them as alpha 1, alpha 1, alpha 2, so on up to what? Alpha 5. These are what? These are the points where you have your function has poles. Okay, and let's also assume none of them are same, so they are all what? Simple poles. Okay, so how can I write this polynomial as that? I can write f of z also as 1 divided by z minus alpha 1, z minus alpha 2. Is this okay? Do you understand this? Huh? Remember? If you know the roots, you can write down the polynomial, right? Just product of z minus alpha 1, right? Good. Huh? Now what is the next step? I need to sum what? Residues at what? At these poles. है ना? Do I need to take every pole? Do I need to take every pole? No. Which ones do I take? Huh? Which ones shall I take? What determines whether I should take a pole or not take?
Whether they lie within the.
Exactly. So what? Upper half, whether they are on the upper half or not. Right? So either I take the, so okay, for this case maybe you can take either, but let's stick to this. So the ones which are lying on the upper half, okay? Huh? So let's say alpha 1, alpha 2 and alpha 3 lie on the upper half, okay? Good? So then this integral is basically what? Is just 2 pi I, right? Limit z approach to what? Alpha 1, z minus alpha 1, f of z. This is the first residue of the first pole, right? I am assuming all the poles are simple. Plus limit what? Okay, I don't want to write another one. Let's say only alpha 1 and alpha 2 are on the upper half, okay? Rest are on the lower half, so you can ignore them, okay? Huh? Good. So, okay, right? And what do you get when you do this? So, f of z is this guy. Don't use this guy. This guy is easier to handle. Z minus alpha 1, z minus alpha 1 will cancel. What do you get? And then you can just put in alpha 1, right? Because there is no problem anymore. So what do I get?
Alpha 1 minus alpha 2.
I get 2 pi I 1 by alpha 1 minus alpha 2, right? Alpha 1 minus so on times alpha 1 minus
Alpha 5.
right? Okay. Then z minus alpha 2, z minus alpha 2 will cancel. I'll have alpha 2 minus alpha 1, alpha 2 minus whatever. Alpha 2 minus alpha 1, alpha 2 minus what? Alpha 3, so on, alpha 2 minus alpha 5. So this is the answer to your integral, basically. This is the answer. You need to figure out the roots, compute the, right? Okay? Right? Just 2 simple steps. You don't need to do any complicated substitution and all. But there is a caveat. What is that? That the circle should go away. Okay? Is that fine?
Yes, sir.
Huh? Is that okay? Huh? Okay. Let's go ahead. Okay, let me just. Okay, good. Huh? Huh?
Yes, sir.
Okay. So let's now. So you know the recipe when you don't have poles on the real line. Okay.
Yes, sir.
Huh? Now we'll consider that there is a simple pole on the real line. What do we do? Right. So let's say you have this integral. you have this integral. Okay. So you are integrating a is, let us say a is real, okay, a is real, okay, and a is, let us say, okay, something, a is real 3 or 4 whatever. Remember, you are integrating all the values from minus infinity to infinity, right. There would be a point when this x will become 3, if a is 3, let us say. At that point the integrand blows up, right. So the value of this integral is ill defined, okay, because there is a point where the integrand just is infinity, okay. In this case you define something called principal value of the integral, okay. It is the same idea that you use for functions. There would be points where functions can just be ill defined 0 by 0, okay, not defined whatever, okay, 0 by 0, but you can still define what, a limiting value, okay, a limiting value. So how do you define a limiting value here, okay. So what point is causing problems, a, right. So we will just avoid a, we will just avoid a, yeah, x is not equal to a. How do we do that? Mathematically what do you do? Your idea is right, but how do you put that thought into action actually? How do you avoid a? So I am integrating from minus infinity to infinity, right. How do I avoid a? Yeah, exactly, we break the integral from where to where? Minus infinity to a, right, but then you have an upper limit, right, a. So how do you do it more precisely? Okay, let me do the step. Okay, now I define something called principal value. So this cross is basically, this is not the integral but the limiting value of the integral, okay. So this is, I define integral minus infinity to a as Naveed suggested, right, dx 1 divided by, then I integrate from a to infinity divided by what, x minus a, good. But there is still a problem. How do you do? Remember, in functions what did you define? If let us say you had sin z by z whatever, and you wanted to know the limiting value as z approaches to 0, what did you do? Limit z approaches. So what do you do here? You will integrate from minus infinity to some point which is arbitrarily close to a but not really a. Do you get this point?
Yes, sir.
And then you leave a bit more gap and then integrate from that point
Left limit of
infinity, exactly. So so can I do this? And what should I do with epsilon? What should I do with epsilon? What should I do with epsilon?
tends to 0.
Exactly. Limit. So I do this guy and then I take epsilon to 0. Okay? If this limiting value exists, I associate that value to the integral. Same idea, like a bit more subtle than that, but same idea as you defined limit function going to 0, limit of a function around at some point where it was not defined, right? So what did I do? I integrated from minus infinity to a to some point very close to a, and then from some other point very close to a but on the other side, and then till infinity. This part and this part, and this is called principal value of the integral. Okay? So do you understand the idea of principal value of the integral? Do you understand? Contour integration gives you a way to compute the principal value of the integral. Okay? Let's see how. Okay. Good. So what did I tell you? That when you have integration from minus infinity to infinity, what kind of contour do you take? When you have integral from minus infinity to infinity, what kind of contour do you take? Real line and then close on a big circle. So I will do the same thing here, but I need to take into account this a point that I am avoiding, right? I am avoiding this point, right? So this is the one part. Okay, let's come back to it later. For now let me just complete. Okay, good. Fine? Huh? Is it all? Huh? Okay, now what do I do here? What do you think? How do I avoid it? What is the simplest way to avoid it? No, this is not a removable singularity. What is the simplest way to avoid this point? So you come, हाँ इसके ऊपर से जाएंगे, right? So how do I go ऊपर से? ऐसे? Exactly. The simplest way to avoid this point is to take a semicircle around it, right? I don't want to take this. It's difficult to integrate over, right? Right? So I take things like this. Okay? So now, good. So now I do the integral over this contour. Okay? So when I do the integral over this contour, what is the first part? Minus infinity till a minus some radius. So first part, so integral or closed contour dz 1 divided by z minus a. Okay? Huh? What is that? First part, integral from minus infinity to what? A minus epsilon. Let me call this r now, okay, or I can call it epsilon, a minus epsilon. Okay, and dz is just dx, so dx 1 by x minus a, right? Plus what? Integral, let's take this part next. No, the circle will come back. What? Integral a plus epsilon to what? Dx divided by 1 divided by x minus a plus epsilon. I am taking this to be the of what is the radius of this guy? Epsilon. है ना? What is the radius of the small circle? Epsilon. Okay, good. Now let's take the small circle. This is a circle centered at what? A. So what is any point on this circle? So z equal to what? Epsilon plus what? Oh no. A plus, so you are here now, plus epsilon e power iota theta. Theta is now this. I hope this is visible. Is this visible? So let me make it bigger here. Theta is this. Okay. So first you shifted so z equal to a plus epsilon e power iota theta. So go to a. Okay, I went to a and then add epsilon e power iota theta. So now I land up here. Okay, good. Okay. Earlier it was just e power iota theta because your center was at 0. Okay, good. Nice. So so what is dz then? Dz is just a is constant. It's just epsilon iota e power iota theta. This is epsilon iota e power iota theta d theta, right? And what function do I have? 1 divided by epsilon iota e power iota theta minus what? A. Okay? This guy. Okay, good. Right? Nice, okay. No, oh sorry, not 1 divided by what? This z minus a. Z is what? A plus epsilon e power iota theta. So this is just epsilon e power iota theta. Right? You have to subtract a from it in the function. Right? Z minus a. Is this clear? Right? There was z minus a. And z is a plus something. So minus a, this a will go and you will be left with this something, e epsilon e power iota. Okay? And what should be the limits? 0 to pi. Just look at the bird. Huh? 0 to epsilon. What are you integrating over? Sir, no, what is the integration variable? Theta. What do you want to cover? Huh? 0 to pi means you are going like this. You are going like this. 0 to pi means you are going like this.
Minus pi to pi.
Minus pi to pi. Excellent. Okay? Huh? Minus pi to pi, only then you will go like this. right, the correct way. Good. Okay, this part is done, and there is what is left? This part, and we'll hope that this part vanishes. Okay, but let's check. Plus, there I know what I have to do, r e power iota theta d theta 1 divided by r theta minus a. This is the guy, right? And what here 0 to pi, because here I want to go like this. Now if r is very large, I can ignore this a.
Yes, sir.
है ना? Right? So what do I get here? Let's fix this part. Let's make sure that this part vanishes. If r is very large, this I can ignore. Okay? No, wait. This guy should vanish. Why is this guy not vanishing? Pi. Okay, why is this guy not vanishing? That r and that r will go. Oh, there is some problem with this. A by r. Does this guy does not vanish, right? And it just gives me iota pi extra term.
Iota pi minus 1.
Huh? Okay, let's just continue. Maybe I can, if I have messed this up, then I'll redo the class. Okay. Okay, let's take r out. Okay. Okay, if r is very large, I can ignore this a. Okay, so this a goes away, right? Then r e power iota theta, r e power iota theta cancels. Okay, and what do I get? What do I get? Iota times what? Theta. Integral d theta from 0 to pi. So what is that? Pi, right? So this is just iota pi. This part. Right? This is an example of what I was saying earlier, that sometimes the integral may not vanish, but you can actually do it. Okay? Because it gave you a simple answer. Okay? Good. Now here let's do this part. Epsilon e power iota theta epsilon, this guy goes. And what do I get? Iota times what? Oh wait, this limit was also wrong. I have to go from, to cover this semicircle, I have to go from pi to 0. Right? Right? So just look at the extreme points here.
But they will cancel out each other.
Here this is pi, okay, and now when you go around till here, it's 0, right? So it should be pi to what, 0. Okay, so then this is minus iota pi. Are you sure? Minus iota pi. Okay. Now these two will cancel each other, is it? Okay, nice. So these two guys go away. Okay. Nice. Okay. So this guy and this guy cancels. Okay. So this contribution, the contribution from this and the contribution from this vanishes. Okay. Right. So what are you left with? Yeah. Okay. Good. Whatever. I can maybe fix it in another class. Let's just follow this line of thought, because this is when I just assumed. So when I prepared the class, I just assumed that this is 0, but now I'm learning that it's not 0, it's iota pi. Okay? Huh? But then fine, this is just cancelling with this, okay, good, let's just continue, okay, maybe we'll learn something eventually, even if we have made a mistake, okay, good. So this guy cancels with this, what do I get? Minus infinity to a minus epsilon dx 1 divided by x minus a plus integral a plus epsilon to infinity dx divided by 1 divided by x minus a. Good? Huh? Is this fine? But then see, now I can take epsilon going to 0, limit epsilon going to 0, because now I can make this circle as small as I want, right? Because what was the purpose of the circle? It was to avoid a. So in the limiting case it avoids a, limit epsilon going to 0. So I can take limit epsilon going to 0 now. Once I do that, what do I get? What do I get? Look, what did I get? What was this called? The principal value of the. I got the principal value of the integral, okay, huh, right? Right, but then it is equal to what? It is the contour integral 1 divided by z minus a, right? But this guy I know how to compute without looking at this epsilon limit. How do I compute? 2 pi I times, no, it's the sum of residues, but there is no residue anywhere, it's regular, so this guy is just 0, right? This should be 2 pi times sum of residues, right? But there is no residue, so this guy is just 0. I think if I have not made a calculation mistake, everything we have done is consistent, okay? So this guy gives me 0, fine, huh? But what if I had something like this, integral, same thing, integral minus infinity to infinity dx f of x divided by x minus a, where f of x is analytic on the real line. So real line f of x does not contribute to any pole on the real line, okay? So once again I define what? A principal value, right? So I define a principal value, okay? So this is basically limit epsilon approach to 0, okay, good, integral minus infinity to a minus epsilon, right, dx f of x divided by x minus a integral a plus epsilon to infinity dx f of x divided by x plus a. This is my integral, huh? But once again, if I do the same contour business, same contour, right, everything will remain same except what now? You will get f of x, right? Here also what? F of epsilon e power iota theta, but a plus f of z would be here, so a plus, right? So what do I get? So I first get, when I do integral over contour f of z dz, or what contour? This contour, okay, real line, bump, real line, and then a circle, okay. What do I get? So I will get the principal value of the integral, because the initial one is just limit, right? Huh? Are you guys following this? This guy, okay, this part, okay, the first two parts would just be the principal value, right? Good. So but principal value of what now? F of x divided by x minus a. This is the first part, okay. What's the second part? Over the bump, integral d theta, theta varies from what? No, theta varies from what? Minus pi to 0 iota e power iota theta, but there is an epsilon, f of z, what z was what? A plus epsilon e power iota theta, right? This was z on the bump, right, on the small circular bump, and in the numerator I have epsilon e power iota. Is it okay? Huh? And what do I get there? Okay, now I have flexibility. I can choose f okay, such that the other one vanishes. Okay. So, I have integral r divided by r e power iota theta minus a f of z. F of z is r e power iota theta, and this goes from 0 to pi. Okay. So, my f can cause this to decay, right. So, let us say f goes as 1 by r, then okay, this and this will cancel each other, right, as r is large, but f will still cause the function to go. So, I will assume f such that the thing on the big circle vanishes. Okay. So, this guy I do not need to take into account. Okay. This guy I can just ignore. So f is such that, right. Okay. So, any simple function would do. F can be, let us say, e power something, e power z. Okay. Is this fine? Good. So, I drop this guy. Okay. And what do I get here? I will get the principal value minus infinity to infinity minus infinity to infinity plus, now this guy will go epsilon epsilon e power iota theta. Okay. Iota I can take common. Now, I have to take limit epsilon going to 0. Okay. So, that will just mean I have to compute f only at a, right. So, this is just f of a times what? 0 minus pi, right, because there is no theta anywhere. Okay. Is this clear? So, when I take epsilon going to 0, this guy and this guy cancels, and when I take epsilon going to 0, this is just f computed at a, and f is assumed that it is fine on real line, and right. And what do I get? But minus, right, 0 minus pi. What do I do? Minus I pi times what? F computed at a. But isn't this the residue? This compute residue of this f of, sorry, there was a z minus a. Can you compute residue of this guy at z equal to a? So, you multiply with z minus a, right. So, this and that z minus a, this z minus a cancels, then you substitute a, because f is okay on the real line, it is analytic everywhere. So, I will get f of a. So, this is just residue. Okay. So, principal value minus I pi times f of a, which is the residue of the function. Okay. Good. Residue of the simple pole that is at x equal to a. Okay. Good. Is equal to this contour integral. But what is this contour integral? You know, there is an alternate way. Instead of splitting, I can just go inside and sum the residues. Residues of what? Because there is one simple pole at z equal to a, which we are avoiding, right? Right. There is one simple pole at z equal to a, which we are avoiding, but there could be poles due to f of z, which I have assumed to lie away from the real line, not on the real line. Okay. So, this is just 2 pi I times s, where s is the sum of the residues of f of z divided by z minus a, which lie above the real line. Okay. Is this fine? And from here we get the principal value. So, the principal value is what? It is 2 pi I this is fine. Okay. Right. Is this okay? So, 2 pi I sum of the residues, okay, but what residues? The residues of not simple poles, residues of singularities of f of z, right. But the residue you have to compute for the entire function, right, because this guy will also contribute to the residue. Okay. So, this is a way to compute residues, this is a way to compute the principal value using this contour integration trick. Okay. So, you take 2 pi I sum of the residues of the function this guy, but then you add I pi the value of this function at a at this point, right, and it came because you took a bump, you avoided this a. Okay.
Yes, sir. Yes, sir.
So maybe we can do next class, because Shabir sir is already here, he is waiting.